Hi everyone, I'm Shreni and this is Lab 4 Oscillations. The purpose of this lab was to compare the motion of the predicted model and observed motion of a spring mass system moving in the x and y direction. We then had to plot the energy changes in the model for various properties like kinetic energy, change in spring potential energy, change in total energy, and gravitational potential energy. To do this, we're supplied with a video of experimental data. We then had to use Tracker to analyze the data and compare our experimental data to our computational model. Some of the guiding principles in this lab are Newton's second law of motion, gravitational force, Hooke's law of spring force, and the work energy principle. First, we have Newton's second law. We can rearrange it to find the final velocity and final positions of the spring mass. And our net force was calculated by adding up all the forces acting on our system, which in this case was gravitational force and our spring force. Our spring force was calculated using Hooke's law, which is on the slide. In our system, our change in energy is a kinetic energy plus a change in potential energy. The potential energy is made up of gravitational potential energy, which is m times g times distance y. This is then added to our spring potential energy, which is 1/2 of the spring stiffness constant times the distance squared. Also, it's important to note that this is a closed system. The system does not exchange energy or matter with its surroundings. Every change is isolated into the system, so the change in total energy is 0. Let's look at our initial conditions. We first have our initial position vector, our average length of a period, which is averaged to be 1.638 seconds, which is calculated by seeing the time difference between each of the peaks in the position versus time graph on Tracker. We computed our spring stiffness to be 5.399 using our equation, and then we also computed our relaxed length of spring to be 0.036 meters. This was found by setting the magnitude of gravitational energy to spring energy, which we will all use in our code. So let's go to our Tracker video analysis. Here's a video we were given on Tracker. As a video plays, you can see that on the right, the position versus time graph is being plotted, and there's also a matching table. We can then export this table as a CSV to be used in our GlowScript code. Now let's look what we did on our GlowScript code. So to our code, we added our initial conditions like mass, position, and velocity, and spring constant, and relaxed length of spring, which I showed how we calculated on the previous slide. We also have to find our length of spring, which is L, and find S, which is the stretch or compression of the spring. So for the next part of code, we had to define our initial energies, then put in our gravitational force and our spring force and our net force equations, which is just grav plus spring force. We also had to use Newton's second law, like in the previous labs, to find our velocity and positions, and then we had to update the position of the spring using these equations. Lastly, we can use this information to calculate energy and change in energy. So these are our graphs we get after running our GlowScript code. This is a position versus time graph. Blue is a computational model and red is our experimental model. As time goes on, there are more discrepancies, probably because there's air resistance in the experimental model to slow the ball down, but not in our computational model. The model over predicts the motion of the spring. Yellow is a total energy, which is sum of red, yellow, and green, and it should equal 0. Blue is our kinetic energy, red is our spring potential energy, and green is our gravitational potential energy. You can see that this does satisfy the energy principle because spring potential energy increases as gravitational potential energy decreases and vice versa. Also, total energy is 0, and this is a closed system, so no energy should be gained or lost. So our next lab question. I estimated that the period of oscillations for both x and y positions by finding the average of the 4 oscillations. So this means it takes the mass 0.2 seconds longer to complete oscillations in the x direction than in the y direction. This is due to the motion of the spring. It moves like an ellipse, so it's wider than short, and this is why x is greater.